We saw in our previous video on slope that slope is a measurement of the steepness of a line. It is a ratio which compares how much the y variable changes, or its rise, to how much the x variable changes, or its run. We can use ratios to compare the rates at which two quantities are changing, and these comparisons are called rates of change. Now, really the only difference between a rate of change and the slope is that a rate of change requires units. All of the values that we calculated in our previous video on slope were just numerical values. They had no units assigned or attached to them. So you can calculate rate of change the exact same way that we calculated slope. So we can use delta y over delta x, or we can use the slope formula y2 minus y1 divided by x2 minus x1. The only difference is that our answer is going to come out as a numerical value, but it will also have units attached to it. Donovan Bailey once held the world record for the 100-meter race in the 1996 Olympic Games. He ran 100 meters in 9.84 seconds. His average speed can be found by dividing the distance by his time. So to find out the speed, we can use the letter S for speed, we'll use D for distance, and we'll use T for time. So if I take the distance, which is 100 meters, and I divide it by the time, which is 9.84 seconds, I get about 10.2, and my units are going to be meters per second. So really it's just taking the unit that was in the numerator over the unit that was in the denominator. So that would be meters per second. So Donovan's average speed then was 10.2 meters per second. This means on average he's able to cover a distance of 10 meters per second of the race. And this is an example of a rate of change because it's a rate that's referring to the change in distance relative to the change in time. So Christine's car broke down and she has to walk home. The following graph shows her distance from work to her home. So in the first part, we need to determine the slope of this linear relationship using the slope formula and the 2 points that are shown. So I'm going to take the 2 points that were given to us, and the first thing that I want to do is label them. So we know that this is going to be our x1 value and our y1 value, and we have our x2 value and our y2 value. So these are the numbers that are going to go into the slope formula. So if I plug my values into their proper spots in the slope formula, I'm going to get 116 subtracted by my y1 value, which is 348, all divided by my x2 value, which is 2, minus my x1 value, which is 6. So if I do the subtraction, 116 minus 348 is negative 232, divided by 2 minus 6, which is negative 4. And if I divide those values, they actually do divide out nicely to give me 58. So the slope of the line in the graph is a value of 58. But there are units attached to these values that were in our coordinate points. So part B asks us now to find the units of our slope. And as a hint, they ask us to consider the units of the numerator and the denominator. So I've recopied the slope formula that we used in part A. And what I'm going to do now is I'm going to go back with those same numbers and I'm going to attach units to them. So if we were to look at our graph, everything that was plotted on the y-axis was actually representative of a distance that was measured in meters. So that means the y values of my coordinate points were distances that were measured in meters. So now, going back to my slope formula, I can actually put those units in. So 116 was actually 116 meters, and 348 was actually 348 meters. The same thing goes for my x values. If I go back and look at my graph, my x values on the x-axis were time values that were measured in hours. So that means the 6 and the 2 were measurements of time measured in hours. So going back to my slope formula then, I can attach units. So this was 2 hours, and this was 6 hours. So when I got my answers, when I did the subtraction, we got negative 232 divided by negative 4. So that negative 232 was actually negative 232 meters. And the negative 4 was actually a measurement in hours. So when we get our final answer of positive 58, it is actually 58 meters per hour. So when we're asked to interpret what this slope represents, what does the value of 58 represent in this context? Remember, we're talking about Christine, whose car broke down, and she has to walk from her work back to her home. So this value that we calculated is actually a speed. And what it means is that Christine can walk 58 meters every hour. So Christine can walk 58 meters every hour. In our next example, Ryan was driving a car at a constant speed on the Don Valley Parkway. And if you aren't familiar, the Don Valley Parkway is one of the major highway systems or routes in Toronto. He noticed that after driving for 1 hour, he had 48 liters of gas left. Then, after driving for a total of 3 hours, he had 24 liters of gas left. Assume in this problem that there is a linear relationship between the amount of gasoline left and the time Ryan has been driving. So in the first part, they ask us to express the information given in this problem as two ordered pairs, where the independent variable is time and the dependent variable is the liters of gasoline left. So it's nice that they give us that information, because we knew now that if we were to graph it, they would want time on the independent variable axis or the x-axis, and they would want the liters of gasoline, or volume if you want to call it, on the dependent axis or the y-axis. So we need to take the information from the problem and translate it into coordinate points. So we've got 1 hour and 48 liters of gas, and then we've got 3 hours and 24 liters of gas. So we're going to write that as coordinate pairs. So remember, in coordinate pairs, your first value needs to be an x value, or whatever information is plotted on your x-axis. So for us, we know that that has to be a value for time. And the second value is a y value. And on our y-axis, we know that that was the volume of gasoline left over in the car. So in the question, the first chunk of data they gave us was at 1 hour, we have 48 liters of gas left. So 1 hour is a time. So that has to be an x value. So I'm going to put that in here, 1. And my y value has to be a volume of gas. So at 1 hour, we have 48 liters of gas left. So my first coordinate point is going to be 1 and 48. So we're going to follow the same model then for the second piece of data. So they told us that at 3 hours, we have 24 liters of gasoline left. So again, 3 hours is a measurement of time. Time is on the x-axis, so the time has to be our x value. So we're going to put in 3 here. And then the corresponding volume at 3 hours would be 24 liters of gasoline. So now I'm just going to go ahead and call this x1, y1. And then the second data point is going to be x2 and y2. So now I can go ahead and proceed to the next part of the question, which asks us to calculate the slope of the line connecting these 2 points. And we have to make sure that we include units in our final answer. So I've got my slope formula written on my page, and I'm now going to input the values of my data points into the slope formula, but I'm also going to make sure that I include units. So my y2 value is 24, and now remember, 24 was a measurement of gasoline, and they tell us in the question that we have 24 liters of gas. So I'm going to go back to my formula, and I'm going to input a capital L for liters. From that, we're going to subtract our y1 value, which was the 48 liters of gas. So I'm going to put in a capital L for liters. All of that is going to get divided by our x2 and x1 values. So my x2 value was 3, and 3 was a measurement of time. And according to the question, our time was measured in hours, minus x1, which was 1, and that is also representative of 1 hour. Okay, so if we subtract 24 minus 48, we're going to get negative 24 liters, divided by our denominator, which is 3 minus 1, which would be 2 hours. And then if I divide that, it will divide out nicely. So negative 24 divided by 2 is negative 12. And my units are going to be liters per hour. So now that we have the value of our slope, which was negative 12 liters per hour, they want to know how long after he started driving will Ryan run out of gasoline, assuming the rate you calculated in part B is constant or does not change. So what we can do for ourselves is make a little bit of a table. So we've got time and volume. So on the screen, I wrote down our rate of change, and our rate that we calculated was negative 12 liters per hour. So that really represents in this context that if Ryan drives, every hour he is using or wasting 12 liters of gas. Remember, we have a negative in front of our rate of change. The negative here just implies that the amount of gasoline in the tank of the car is being lost or decreasing every hour that passes by. So I went ahead and filled in some numbers under my time column. Okay, according to the question, the first amount of data or the first real value that they give us is that at 1 hour, Ryan had 48 liters of gasoline left in his car tank. And then at 3 hours, he had 24 liters of gas left. So we know that every hour that passes by, he uses 12 liters of gas. So that means that our volume every hour should be dropping or decreasing by 12. So they did skip a value in the in-between. They gave us an answer for 1 hour, they gave us an answer for 3 hours, but they didn't give us anything about what happens at the 2-hour mark. But we could calculate that ourselves because we know that if he started with 48 liters of gas, by the next hour, or at the 2-hour mark, he should have lost 12 liters. So we could just do a simple subtraction, 48 minus 12, which should give us, I'm going to use a different color here, that should give us 36 liters of gas. And then 36 minus 12 liters for the next hour brings us to 24 liters. And then we're just going to keep that pattern going by subtracting by 12, and we want to figure out how long is it going to take for Ryan to run out of gasoline. So we want to get the volume of the tank down to 0 or as close to 0 as possible. So if I continue subtracting, 24 minus 12 is going to give me 12 liters at the 4-hour mark. And then if I subtract 12 again, 12 minus 12, oh, it's 0. So at the 5-hour mark, Ryan will have run out of gasoline. In this final example, we are going to take the information provided to us and we are going to calculate the rate of change for each scenario. This is a good question because it really tests if you know how to assign variables to the independent axis or the x-axis or the dependent axis or the y-axis. Once you know which values go on the x and y-axis, then you can assign them x1, y1, x2, y2 designations and then plug them into the slope formula to calculate the slope. So in question A, it tells us at 3 weeks old, a corn plant is 4 centimeters tall, and at 15 weeks, it is 46 centimeters tall. So if we had to think about what would be independent here and what would be dependent, we've got an age or an amount of time. So that's the 3 weeks old and the 15 weeks old. And then we've got what looks like a height of our corn plant. So at one point in time, it is 4 centimeters tall, and at another point in time, it is 46 centimeters tall. So 3 weeks and 15 weeks, to me that is a measurement of time, and we always know that time is plotted on the x-axis. So that means that the 3-week-old and the 15-week-old information, those are going to be x values because time is always on the x-axis. So then automatically I know then that this 4 centimeters tall height measurement is going to be a y value. And then the same thing goes for this 46 centimeters tall. So I'm just going to take the numbers, match them up, and create coordinate points. So my first point then is going to be 3 and 4, because at 3 weeks old, my plant is 4 centimeters tall. And then my second point is going to be 15 and 46, because at 15 weeks, my plant is 46 centimeters tall. Okay, so I labeled my points, and I'm ready now to substitute those values into my slope formula. So just in the interest of space, I'm going to work across the page or across the screen. So my y2 value is 46, but remember we need to include units. So according to the question, 46 as the height was measured in centimeters, and we're going to minus our y1 value, which was 4 centimeters. Put in the bar. My x2 value was 15 weeks. I'm going to use WK just to represent weeks, minus my x1 value, which was 3 weeks. Okay, now we're ready to subtract. So 46 minus 4 is 42 centimeters. Divided by 15 minus 3, that is 12 weeks. So if I divide 42 divided by 12, it's about 3.5 centimeters per week. So that just tells me that my corn plant can grow on average 3.5 centimeters every week. In question B, after driving for 4 hours, Tom is 82 kilometers from home, and after driving for 7 hours, Tom is 224 kilometers from home. So again, I want to look at my numbers and figure out what would be plotted on the x-axis, what would be plotted on the y-axis. So again, we've got 4 hours and 7 hours. Those are measurements of time. Time is always plotted on the x-axis. So I know then that the 4 has to come first as an x value, and the corresponding value that goes with my 4-hour time mark is 82 kilometers. So my first data point is going to be at 4 and 82. And so then my next data point would be at 7 hours and 224 kilometers. So I've labeled out my data points, and I'm ready to substitute my values into my slope formula. So my y2 value is 224, and the units attached to that was kilometers, subtracted by my y1 value, which is 82 kilometers, all divided by my x2, which is 7 hours, minus my x1, which is 4 hours. So 224 kilometers minus 82 kilometers is 142 kilometers, all divided by 7 hours minus 4 hours, which is 3 hours. And 142 divided by 3, it's not going to work out to be a nice whole number. Okay, you could choose to leave it as a fraction, but because this is a real life, real world example, writing your final answer for something like this as a fraction doesn't necessarily make a whole lot of sense. I mean, it is totally a valid number, but we want to translate it into something that is applicable for someone who is driving in a car, let's say, and going home. So 142 divided by 3 is roughly about 47.3 if I were to round to the nearest tenth. And then my units would be kilometers per hour. So if we had to interpret this number or this answer as a rate of change, I could say then that Tom is able to drive about 47.3 kilometers every hour. So the key takeaway from this lesson is that rate of change and slope are calculated in exactly the same ways. You could calculate a rate of change from a graph using the rise over run method. You could calculate the rate of change from a table of values if you wanted to use the delta y over delta x method. You could calculate the rate of change using 2 points and using the slope formula, y2 minus y1 divided by x2 minus x1. The key difference here, though, is that your answer for a rate of change is going to be a number that has units attached to it. The units are going to come from the question itself and whatever the scenario happens to be in that particular question. And then you can take your answer and interpret it, just like we did in our previous question. We knew that Tom was able to drive for 47.3 kilometers every hour.